So now that we know a little bit more about dissociation equations, it's important to try and figure out how equilibrium actually fits into this whole thing. And I think you can probably see the connection already that with our insoluble, or I should say quote unquote insoluble compounds that have a dissociation equation that features that double-headed arrow, that implies that equilibrium is going to be part of the math of how we come and calculate these concentrations. So it's kind of not always super duper possible or convenient to kind of on the go make a saturated solution to calculate a molar solubility of a material. So what scientists have actually done is they have tables and tables and tables, not necessarily of molar solubilities, although those do exist. They actually have these other calculations called KSP values, or equilibrium constants, which take into consideration the temperature of a material. Because remember that K value will change with temperature. Generally speaking, we've seen now that K values will increase with temperature and K values tend to decrease with temperature. So what do they actually look like? So here is our dissociation equation for calcium carbonate dissociating into water. And again, it's important to remember that we have that double-headed arrow. The implication behind that double-headed arrow is that we are in a situation where equilibrium takes place. So if equilibrium can take place here, then we need to write an equilibrium expression. And in this case, don't forget, it's products divided by reactants. So I'm going to take the concentration of the calcium times the concentration of the carbonate and then divide it by the concentration of the calcium carbonate. Well, you might be saying, hey, wait, hold on, Dono. I thought we had a solid on the inside of our equation. And if you caught that, you are in fact correct. Remember that the activity of any solid, or any pure liquid for that matter, is 1. So we can actually simply cancel this lovely solid product out of our material completely. So our equilibrium expression actually simplifies to just the plain calcium and the carbonate. Now it's important to remember, again, this is called a dissociation equation, and it's used to show what specific parts of our compound are actually going to dissociate into that water. Let's simplify up our equilibrium expression. And because this is actually talking about a soluble type material, we are actually going to call this equilibrium expression, this K value, KSP. Now, SP stands for the solubility product constant, or the equilibrium due to this solubility. So the solubility part comes from the fact that we're specifically dealing with dissociation equations only. They're all going to look the same. It's always going to be a single solid ionic compound splitting up into its pair of ions, its cation and its anion. So for all of them, you're always going to see that solid reactant, not part of the equilibrium expression at the end. It's only ever going to be a function of the product or the multiplication of the concentration of the ions in that solution. Now, it's very simple to calculate. It's all just plug and chug math. So for example, if we knew the molar solubility of the calcium carbonate was 1.3 times 10 to the negative 4th molar, then the concentrations of those ions is the same, and we can just simply plug them in and chug out our final value. And in this case, our KSP value is 1.7 times 10 to the negative 8th. Now that is a constant. That's the solubility product constant. And that is again going to remain constant for that specific temperature. It will change with temperature, because again, ionic substances tend to be more soluble in warm temperatures and less soluble in cool temperatures. Now, I want to compare and contrast this with a second equation, something maybe a little bit more interesting. Here is an equation for copper 2 hydroxide, which is pretty insoluble. I'm not going to put up any values this time. I just want to look and see how the expression itself is going to be generated. Again, the reactant, the copper 2 hydroxide solid, is not going to show up in the equilibrium expression. It's a solid. Its activity goes in as a 1, so we kind of ignore it. But instead, we can put in the copper and the hydroxide. Now notice the specific difference here. Don't forget, and this is the most common mistake made by most students, the coefficients become superscripts here when we actually calculate these lovely KSPs. Now, in the next sequence of videos, we're going to focus on the two major types of KSP calculations, and they're reverses of each other. We've seen that time and time again where we have a type of problem where we can do something, and in a subsequent type of problem, we can undo it. So we're going to go back and forth between two numbers. One, using molar solubility, or the amount that can actually dissolve, to find KSP. And then a second where we actually use KSP to go backwards to find molar solubility.